Welcome to Notes number 7, Statistical Reasoning, Part 2. In this version now, we're going to be delving a little bit into a few new terms, sampling, sampling size, the idea of sampling methods, and then also going over interpreting statistics that you see through journalism that are related to science, ethical issues, and some misconception of issues that need to be taken into account when you're interpreting information, but also when you're designing things within your experiment. So let's begin. So we've seen this multiple times now throughout this entire course, and this is the basic algorithm or steps or procedure that we are using for the scientific method. That built into it again is that logical reasoning of that sequence of steps that you're going through to build up your argument from the very beginning of asking a question and all the way down to analyzing your results and then communicating those results. And as you learn through that process, gain new information and innovate off of your ideas as you go. And we had that first step. We talked about asking a question, doing your background research, constructing your hypothesis. And then we need to deal with setting up and designing your experiment procedure. And we've had a little bit of this so far of talking about your control variables, the steps you want to do. But we need to worry about, again, how are we gathering our empirical data and how that will impact our analysis afterwards. So we need to know about stats and understand it to help us also design and analyze it. So some of these notes will help answering sample size methods and how many data points you should gather. If you're working with people and you have a whole population and you only want to sample a small bit of it or sample a smaller item from your population, then maybe how could you go about doing this? And then finally coming down to the idea of analyzing it and also within your design is some of those misconceptions of what bias and other things are you placing within your design or a scientist is placing it, and interpreting information, ethics, and all these extra other stuff we need to take into account when analyzing or designing anything that relates to science. So, begin with a few new terms. And what does it mean within the realms of statistics and then also science? So I've mentioned the term population before. And generally here, population, most people probably start thinking, of living things, of creatures, of people, the population of Calgary, population at Mount Royal, so forth from there. But in statistics, population refers to the entire pool from which statistical samples and data will be drawn. So this is out of everything. And so it can be an entire group of people, or it could be objects and events, hospital visits, wait times, or a group of your measurements that you're looking at or you've gathered or you're analyzing. So overall, this really refers to that population, gives a term to talk about this overall thing that we're pulling data from. And a population can then be said to be an aggregate of observations of subjects grouped together by some common feature. So there's something that relates them together in some way. So if we're thinking as all humans on Earth, well, it's humans that exist or are alive, or all alive humans. Or we're talking about population of Calgary, well, it means all people, say, that live in Calgary or working in Calgary or are currently in Calgary at this point in time. Depends upon what you're trying to look at. And so it'll be some kind of underlying thing that groups these together and becomes kind of like your population of a bigger whole to represent all the little bits that are inside of it and whatever common features you have there, and generally relates to your project you're working on. And something you need to take into account is that whatever you decide upon, or your question, your hypothesis, you have to think, well, what is then the population that relates around that question? Who relates to it? Like in the case study for the student designing things about the effect of age on color, when they decide to look at Mount Royal specifically, then it means, well, the population that they're looking at overall is every student that is at Mount Royal. So this overall, so that narrows it down, needs to define that. You need to think about that when you're designing your own case. So it can be defined by many different kind of characteristics and whatever you draw upon, but it's really key upon what you're looking at. And it can be vague to being more specific. So say a vague example Could be the number of newborn babies in North America. Or say the total number of tech startups in Asia. Now it's a little bit vague because North America, large region. Even more vague would newborns in the entire world. And this is getting a little bit more specific. Or like you can get more specific by saying, say, the number of newborn babies in North America with brown eyes. Or the number of startups in Asia that failed in less than 3 years. And so that's kind of helping narrow stuff down. And sometimes, depending on what you're looking at, maybe a vague population in your sample won't really work good to the specific question you're working on. If your specific question is grounded in a specific locale or area or topic, well, maybe your population that you're going to sample from needs to be narrowed as well to better represent the type of question you actually have. Or so being more specific. Or maybe the population you're looking at is too specific when your question is a little bit more vague and needs a wider case. And by you being specific, you're adding in bias into the sampling pool that you may have done everything else right, but just the fact that you limited the pool that you're sampling from has introduced bias that you may be expecting a specific result to come out. And most times, statisticians, researchers want to know the characteristics of every entity and element within the population, but this sometimes can be impractical. If it's, say, 10 items, maybe they can process through it. Maybe it's 1,000, they have that time, but you start going into 1 million, a couple 100 million, if it's 1 billion, maybe that time is not possible with the tools that they have, and can be impractical coming with larger sizes. Because, we'd want to have everything. If we know every element, we'll have more empirical evidence that's more narrowed down that represents the population exactly. But there's other factors that come into play. Like if we're looking at all students at Mount Royal, maybe it's really difficult to get every single one of them to actually, say, respond to a survey, or for you to track down each one individually. And the time it would take may go beyond the scope for the project. And then by the time you get all the data, everything's outdated. And then what do you do from there? So maybe you want to look at, say, only a few people. And then question, well, who, and how many? And how would that affect the overall results? Should I only talk to one person? Should I talk to 90% of them? Should I only talk to them from one group? Well, these are questions you have to take into account as part of that actual design. So let's go for an example. If a company wants to know whether each of its 50,000 customers' service during the year was satisfied, it may be challenging, costly, and practical to call each of these clients on the phone to conduct that actual survey. That's 50,000 calls that you may not get through to everybody, and who's willing to actually answer that, and how long it would take to maybe convince people who didn't want to actually answer that, and gathering that data. You cannot measure everything. There's time and constraints, and it really wouldn't be productive. Maybe by having a smaller group, you'd get close enough of an answer that may not be perfect, as long as you're not introducing bias by not sampling enough and not talking to enough people and who you specifically talk to. And so you need to deal with those questions again. So this is where we get to another term that's very important, is sample or statistical sample. And a sample refers to a smaller, manageable version of a larger group. And generally this means that larger group is coming from your population. So you identify your population you're looking to that relates to your project, and then you want to decide, okay, can I review all of those entities? Well, if yes, then go ahead with that. Otherwise, if it's too large to go through every single entity within that population, then you need to make a sample and decide upon how you're going to sample. So how do you select elements from that overall population, and how many of those elements do you actually select, and trying to deal with a proper design. Because again, if you don't, you're kind of making a weak argument, and you're also weakening your case for establishing causality. And so when it comes to that third clause that we've been talking about for non-spuriousness, is that maybe from right there you're already introducing like a case where your subsampling doesn't show other cases or proper data and breaks your argument. And this can happen in many cases, even stuff that can get published. It should be validated and checked. So samples are used as testing populations too large with too many observations, and you should represent that population and reflect any bias towards a specific attribute of that one. So you're hoping that you're not self-selecting people just to get your point across and turning from testing your hypothesis and changing it around to being proving, where you're not doing anything right, that you've already decided what the answer is, then you're only gathering data that fits to what you believe it is, and not trying to challenge your own beliefs by having what is the overall objective nature of that data in these cases. So researchers may have problems gaining ready access to the entire population of the reason for samples, and you have to understand the nature of the actual studies. And these are all the reasons why you want to sample instead, that it relates to it. If we're working with plants and testing this, well, maybe it's how many plants we have, which relates to an actual sample. It could be a fictitious larger population. We can manage checking all those plants. Versus working with people, is it really possible to get the exact number and measurement of what you're looking at versus a subsample to get an idea? So using a smaller number of people who represent the entire population can still produce valid results while cutting back on time and resources, as long as you try to make sure you're choosing the proper sample method and you are using a proper sample size. And the fact that it also properly represents the actual population. So this is part of the sampling method that we're going to be coming up to. That all participants in the sample should share some characteristic or quality. So they would have the overall characteristics you're looking in, the overall population should be mirrored within there. But if there's differences within the population beyond just that one characteristic, how are you also taking that account not to oversample one group versus another? So, for example, if the study is about male college freshmen from right here, so that's your overall population, then your sample should be some percentage of males that fit that description. So they must be college, they must be freshmen. So being new students, you must define what range defines being those new students, and if it's age or if it's just year that they're coming into school and what factors those are, and making sure that you sample from there, maybe even what school you're looking at. Say also if a research group conducts a study on the sleep patterns of single women over 50, then the sample should also reflect women with this demographic, that they're over 50, that they meet what you're specifically looking at, and that you should communicate that's where you sampled from and drew your data, and how you can make those kind of connections. Even another example. So consider a team of academic researchers who want to know how many students studied for less than 40 hours for a major accreditation exam, such as a CFA, and still passed. And suppose that more than 200,000 people take the exam globally each year. Reaching out to each and every exam participant may be an extremely tedious and time-consuming thing. So here your population of people is looking at an accredited exam where there's a potential 200,000 people across a global scale that take this, and you're trying to look at the cause and effect of studying less than the amount of study time versus passing the exam, and in this case, narrowing it down to less than 40 hours, and if that resulted in passing exam. It's more of a prediction built off of a hypothesis. And reaching every single one of them is just not going to be practical. It's 200,000. If you had the money and time to do that, it's going to be difficult. So you need to start thinking of some kind of subsample that you're working with. So, in fact, by the time the data of this entire population is collected and analyzed, a couple of years could have possibly passed, making analysis worthless, since a new population would have emerged. And so this being that by the time you collected from the initial people who are taking these exams, within that range, by the time you've collected it, there's a whole new group of people, maybe a couple of years later, that are now taking that exam. And now, how are you drawing this? How do you keep doing it when it takes too long in the future, and then taking the time to do that? So we need to pick that sample, need to decide what size and how to do it, and be careful not to add bias into the sampling. And to give a better definition of that, sample bias here, in statistics, sample bias is a bias in which a sample is collected in such a way that some members of the intended population have a lower or higher sampling probability than others. So basically you picked more of one group versus the other. And this is you're selecting bias. Maybe you didn't mean to, but you only selected a few and you didn't realize the different demographics of the population you're looking at, for if these are objects or wait times or people or locations, whatever. Just not So here, so what do you get from this? And you can see that picture that we've got up here is like, well, you can see if we're looking at the overall population, if we're representing demographics, that like, okay, we got these circles, those are each element within that population that we could potentially sample from. But you can see here, well, there's a lot of whatever the red characteristic represents, but there's a lot of that red characteristic versus the actual green. So at the top, so the larger green versus the actual red. And if we sample here, like, oh, look at the sample, there's very few red and a lot of green. Well, then that's wrong. You like work with a sample that doesn't also reflect like roughly the breakdown of the overall population that we're working with. And so you need to be careful about what you're doing from there and how you get these and what you have access to. And it may not always be exactly perfect, but it shouldn't be margins or scales off. Otherwise, the conclusions you can draw based upon that data will be invalidated just based upon the way that you sampled. And that's something you should be looking at if you're looking at studies or how they're reported. What were they actually looking at? And then what were the final claims? And how can you draw and make conclusions from that? So let's do a little thought experiment for a time. So looking at ourselves at Mount Royal, and let's assume that there's a study that's being done to determine the eating habits of first-year MRU students, and the following samples are proposed from different populations. And see, these are all first-year students and where their eating habits and how they eat. And like, well, we know we have to look up exactly how many students we have, but there's always been a range of like 12 to like 14,000 students overall, and we have to see how many of those are first years. And then from there, decide what we look at. And, well, what if we looked at only sampling from, say, football teams or sports teams? And you can pause and think about, like, well, what are the eating habits of, like, individuals who do lots of sports or working out? My own experience with it is generally a lot. It's very controlled eating for what you'd have, the physical nutrients that you actually need from there, and taking into account of building your body and when you eat and how often you eat. And is that really representative of every first year? Because not every first year is going into sports. Like, I definitely don't. And like when I went to first year in my undergraduate, and there's a lot of others that they don't do that time. So is that really good representative? If we only sampled or oversampled from there, that would really only mean like, well, if we were looking at first year eating habits of MRU students who are also in sports teams, well, then that's a good population to sample from. That's good here. But here we're talking about all of MRU, and like, well, we'd have to look and see how many students on MRU are actually on sports teams. What's the proportion? And then we should sample in relation to that if we're able to find that information, or just try to be careful. Say a class of computer science students that I know well that sometimes don't always have the best of eating habits, maybe, if they do and what they do. So, and you're like, well, the school is not all just computer science students. There's lots of other students, and is there differences from there? And should we only look at them? I'm like, nah. Say required gen ed course? Maybe. Maybe we don't get everyone, but say this course itself, I generally get people that are in their first, second, third, and fourth year. But there's usually a lot of first-year students who take it. There's also not just one group. I get interior design to criminal justice studies to business students, psychology students, science students. So it's a good chance I'd be sampling it, but I wouldn't want to only do my class. I'd want to look at other classes because is mine the only one that's needed. Also could look at, say, what about all first-year students living on the dorm? I'd say, well, how many students are actually living in the dorm and how many cook for themselves versus they don't? Or if you're living at home, how many of you cook for yourselves versus not? Maybe if your parents or sibling or someone else that's living with you is taking care of that, maybe they control more of it and changes these patterns. These are all different groups we don't know, but like if we oversample in any one of them, it's going to have to affect. So we'd have to see, well, what's the ratio that we have if we're able to find out how many people live in dorm, how many people live at home or on their own, and if we have access to how many sports. But generally, we want to do a wider sample across this and take into account not to look at only one group. Or if we were narrowing our question, like I said earlier, if you're looking at MRU students, first-year MRU students who are on sports teams and their eating patterns, and we also then include like computer science students that aren't sports like anyone outside, well, that's going to have an effect on the actual data. And that sample has to represent the proper population that you're actually looking at. So it's an interesting thought. So when you're designing, you take that into account, and when you're interpreting anything through journalism or into the papers, you also have to understand how does the potential population of students they're looking at, how they sample and how they report those samples relate to what they could draw out of it. So, types of sampling. We will not go into this deeper. There can be entire courses in stats on this in science. I just want you to give you a feel for it and be aware that there are sampling methods and that you should talk about your sampling method and have a route of how you can start discovering where to go with. So just like when we started with stats and we had descriptive and inferential statistics, and then you could break it down from there, is you need some guiding posts of where to go to search for terms and build upon this. So again, the process of deriving a sample is called a sampling method. So you define what is your population first you're looking at, and then you're defining the right sampling method for how you will pick elements from that population to include in your sample or groups of samples that you'll be including to gather data from. And it's an integral part of the research method and everything in quantitative and qualitative design. And so there's different ways you would go about doing that sampling. But the two general types that you will get, or distinct approaches, is either probability sampling or non-probability sampling. So two families. Now, probability sampling, as you get, is more like randomly. So sampling utilizes random sampling techniques to create the sample. So you define your population from entities from there. You have some mechanism or procedure that you go about to pick each one randomly. And how you're doing them, that's defined. And then from there, and knowing the size, then that's where you get your specific subsample you're working at. So this group of sampling methods gives all the members of a population equal chance of being selected. So not every entity will be part of it, but they're given equal chance, and they're using some other tool to generate a random choice or procedure to help them pick. So probability sampling gives you the best chance of creating a sample that is truly representative of the population. Using probability sampling for finding sample sizes means that you can employ statistical techniques like confidence intervals and margins of errors to validate your result. So those are terms, again, that we're not going to go into this course. It's more from stats. And these confidence intervals is more calculations that you can do on the data. How well do you believe like your sample reflects the overall population? And the margin of error of whatever the answer is, how far off that would be. So kind of the spread, and the fact that we're getting back into the quantitative kind of numerical speak and mathematical speak and science that becomes important, that when I say confidence intervals, knowing that this is going to be a numeric generation, some data you're actually going to get and being able to interpret it from there and back up your argument based upon it, which goes back all the way to your empirical evidence or the way you're sampling or your population itself. So example, the very first one, very simple one. So from that family of probability sampling, you get simple random sampling. Right here is the most straightforward way of selecting a sample is simply random sampling. In this method, each member has an equal chance of being part of the study. The object of the sample population are chosen purely at random bias, so maybe by flipping a coin or rolling a die, and each member has the same probability to be selected. And so you're hoping from here that overall that how you're picking that probability choice of including them right here is that it's not you picking it, but it's some kind of other choice coming here. And in the end that you have hopefully something that has a proper representation. And now an impact on this is going to be that sampling size. If it's too small and you're randomly generating it, maybe you're going to randomly overly select one part of the population. But if you pick a large enough or proper enough sampling method that's still feasible for you to do your work with, but within the realms of proper error margins, then, well, the random sampling will work properly to pick out hopefully a close proportion of it with the range of errors you could get. And you should be leading up to this as generally a mathematical calculation we won't go deeper into in this course, but you'll see it coming up. So say, for example, where a study could be used is if a university dean would like to collect feedback from students about their perception of the teachers and level of education. And there's 1,000 students, say, at the school. All 1,000 students at the university could be part of this sample. Any 100 students can be selected at random to be part of the actual overall sample and maybe a more feasible way to get feedback. I say even if it was even larger. Got to remember to take pauses in between the slides. I forget that when I'm not teaching in front of people. So the other family of types of sampling methods you get is non-probability sampling methods. And you can kind of guess if it's non-probability, means it's non-random, and there's something more coming into this. And some of these would fit a little bit better in sciences, if not a little bit better in the qualitative research kind of methods. So non-probability sampling methods use techniques where the samples are gathered in a process that does not give all the individuals in the population an equal chance of being selected. So it doesn't mean that you're doing bias. You state that you're doing non-probability sampling methods and which one, and if that fits properly within what you're looking at overall, then you decide maybe it's based upon your own experience how to pick this. Now, in the majority of cases when it comes to science, the probability sampling will be the better choice. But if you're in the beginning just trying to get a sample, to get an idea to maybe build up a correlation before you go past this, then well, maybe non-probability sampling will be a first step so you're not spending too much resources or time or budget into what you're looking into to get a first feel, kind of like dipping your toe into the water to feel the temperature before just jumping right in, if it's scalding hot or freezing cold, depending upon if you want to stop yourself. Then, well, maybe there's the first step. And then qualitative, well, maybe because, the groups you're looking at and the stories, you're gathering and that evidence. And as your experience as a person, maybe part of that group, you know what to look for. So so you see again, like these types of sampling can be used when demonstrating that a particular trait exists in a population. It can be used when a researcher aims to do a qualitative pilot or exploratory study, so not cause and effect, but just seeing what's out there. And when a researcher has limited budget or time within the workforce, you have to get some data out of this. The reality of time with all of us to finish everything. So using the researcher's discretion to sample is also a case that, well, maybe that researcher has years of experience and knows the proper population or area to work at. So especially with a qualitative kind of research versus the quantitative or numbers. Primarily for research where object is to derive hypothesis about the topic in research. So again, the probability sampling methods when it comes to this course and Laws for Science is that's what you'd want to go for in picking the right sample size that you're working with. Whereas if you're in qualitative research, well, maybe some of the probability sampling methods can work, but you'd also then sometimes want to narrow down to the individual story of sampling one person that has that story, like talking to an elder from a culture that maybe has more experience if that's what you're looking for. So an example from non-probability sampling methods is convenience sampling. The sample is taken from a group of people easy to contact or reach. For example, standing at a mall or a grocery store and asking people to answer questions would be an example of a convenience study. So maybe standing by Wickham Hall to ask if they're a first-year student and their eating patterns. But sometimes if you're going to Wickham Hall, maybe you're not going for the best of eating patterns because I don't know how much healthy food is still there. Or ranges are what you consider. So maybe sampling somewhere else in maybe the main hallway in Lincoln Park because wide ranges of people go through there and back and forth. Who knows? But the example of that convenience sampling, you can see this comes up and getting a feel for what's going on. So we have charts here, so this gives you a better idea, and I just want to show that breaking down of the families that you can start with, like all the sampling methods, and you're getting that probability or non-probability as subcategories, and then from there, those break down to others. You saw like probability, we had the simple random versus the convenience, but you can see here there's examples of others from the probability of systematic, cluster, stratified, or maybe non-probability of quota. These are again just terms and things to get used to. As well, if I know that there are sampling methods and I know that there's a family of probability and non-probability, well then I can decide, do I want to use probability sampling or non-probability depending on my project, and then from there start researching specific sampling methods under there and how to do them and looking up for similar like research studies of like, okay, well, how did they do it and how can I do it, and getting more in depth with the language that you would actually use. And that's the point of these notes. So determining the sample size. I mentioned it a couple times. It's not like you want to get your population and get that right. You want to make sure how you're sampling from your population, if you need to do samples, is done properly in the method you're going to use. But then you need to worry about sample size of, well, How big is the population, and how big should my sample be? And deciding upon that question. And again, if this is science and quantitative, there's calculations for that based upon data that you can get, and it goes more in depth. But we need to get to some notation that you'll see sometimes. It could be different across the board, but most times you should see things like, well, if there's a capital N, that represents the entire population size. So if the population was all people in Calgary, then N in this case would be the population size of Calgary. If it's Mount Royal, then what's the population size of Mount Royal is N. If it's a number of geological samples that you've actually taken for entities in an area, then that's N. Now, and that's capital or uppercase N. Now, lowercase n represents the sample size. So how many of the actual overall population, how many did you actually sample possibly from there? And it's convenient, it's the lowercase n. So it's a nice, easy way to remember it. Uppercase N, the big whole thing. Lowercase n, the sample of the bigger thing that you're actually looking at, and making sure that you've represented it right. And then we want to make sure that, well, if capital N or overall population from here, what is our sampling? Is it equal to, they're both equal to each other, so we're just doing the entire population, or is it less? Then how little is too little versus too much in time, and being careful about this. And really in this case, this course worrying about that is too little, that's too small to really draw any conclusions from. Looking at one plant, looking at one rock, looking at 10, looking at 100, looking at 1,000, we have to decide upon that. So sample size determination is the act of choosing the number of observations or replicates to include in a statistical sample. So replicates from right here is being like if we're working with plants, how many of the plants should we actually have? So we just do work with one, or do we work with 1,000 copies of the actual plant and measure each one? Sample size is an important feature of any empirical study in which the goal is to make inferences about a population from a sample. It's an important thing. You should be seeing it when you're reading anything where they talk about. You should know that if they've done any study from this should be behind it in some way, and you should be able to track that down and make sure, is this properly represented? Can you draw those proper conclusions? So in practice, the sample size unit study is usually determined based upon the cost, time, or convenience of collecting the data and the need for it to offer sufficient statistical power. In complicated studies, there may be several different sample sizes that you'll work with. So here for the cost, time, and convenience of being able to do it, you have to factor in knowing your population, how you can gather the data. But this term here being statistical power means, well, you need to take into account how does that size relate to the overall population and back to stats and measurements that you could do. And so that back and forth. Because too small of a sample will result in a case where you do not properly draw inferences in regard to larger population. So you could be making an argument, said you did a sample, collected your data, analyzed it, and come to some conclusion, and then someone else comes back and they go through your logical sequence steps that you've been doing to get to your actual argument, and then realize, well, hey, this population, say of Mount Royal, has 10,000. You talked to 2 people that you met in one hallway on one day. How does that represent everyone on those campuses? That doesn't, so it's too small. So your inferences you can't draw from there. And so you may be reading and seeing the end result of communications through journalism. You have to realize, well, what's behind there? Maybe I should question that, and what's their sample size, and know that it's actually there. So calculating it. Formulas. Don't be afraid. You do not need to memorize this formula. Again, I just wanted to bring forth an artifact that's saying that these things are calculated. You have formula, you have variables for this, and you can calculate a lot of other information, but this is one that we need to start learning more. Like, you have to know what's your population size overall. And there is formulas where if you don't know the population size and just infinite, they take that into account. Things you have to look up, things like Z-score, which is just another formula, another calculation based upon the actual data. Your margin of error is also a calculation, and the standard deviation we've kind of talked about before is that kind of spread that you actually have over all this, and if it's working with the normal distribution. And so then if you're like, okay, well, if I have all these pieces of information, you just plug it directly into the formula you see below, and it gives you back, this is how many samples you should actually be doing, and making sure that you're picking everything right. If you want to dig into this a little bit deeper, you can go and look at this link here, which goes over a basic overview of it. But I won't require it for this course. It's just to know that it can actually be calculated, and there are cases where you need to be careful about it. Now, if it comes to this course, like for this course, we will not go as far as fully calculating the required size. And if you needed to use something, you can just use an online calculator like the link that I've provided here to decide upon that. And you just have to imagine, like, we're just going to assume like we're basic starting out. We know we're not going to be perfect at what we're doing, so we'll just try to. We'll say how we picked our sample and what our settings and margins were. We can say the tool we used even to actually calculate that, so someone else can validate these numbers, and then go from there based upon the number it gives us. And then someone else maybe can correct us in the future, knowing, okay, no, you need to dig into this a little bit deeper, know this a little bit more, and change these things around. But at least they'll know where to pinpoint to help with that guidance. But at least we can also then back it up by, well, we're following these steps. So I've included an example screenshot from that actual website here. And so what we'll say here is, like, I just left everything that was in there like standard to what it said, the confidence interval. And like, if you look at that website, it also tries to explain this a little bit more to you, and you can use these terms to realize, again, these are all statistical terms, so I should be able to dig down and find the tools and formulas and explanations for how to interpret, how to use them, and do work with them. But here I just left everything, the confidence interval, the margin of error, and the population proportion, just to what they left it at, and just said right here, okay, what if I was looking at overall population I knew was 2,000 elements. And you can see here, if it was unlimited, you don't know what it could go up to, you just leave it blank. But here I put 2,000 elements, and it using, and basically this one uses this formula that you see here and these other steps to come up with this number, and says, okay, well, if I have 2,000, then try to at least sample, like, at minimum 323 samples from this. And so what this means, like, the 95% confidence level is that if you're sampling and the answer you do get from this is that you're 95% sure that this is right, and there's a margin of plus or minus within a range of 5% from your answer that okay, this isn't actually working and could be wrong. So the variance that you have overall from that. And so to get these numbers, you can calculate it, and the population proportion is, like, what do you expect from there? What you're sampling. But I don't want to go too deep into this, because that's not the point here. We're dealing more with the quantitative reasoning and realizing, well, within this reasoning and designing our experiment, we have to know to pick the right population, not be over biased in our sampling, be clear about our sampling method we're using, use random, like the probability sampling, and use those methods, and then pick the right sample size to then step forwards with. Ooh, it's a lot there. 37 minutes, still going, but it's not too bad. We're building on a lot of previous information. Now, in a few of the previous slides, the term statistically significant has come up. And so this is another one of those science cultural terms that is really important to understand and be aware of when you hear that in journalism, when you hear other people talk, and just as if you're in a cultural gathering in a market and you heard key terms, you understand that was important for that area and for that group, then you're like, well, if you hear statistically significant, then that's also really important for what does that mean in relation to science? Because many people could misuse this. Sometimes people just break it down, well, and I would do this too, and this is not improper if I didn't know a word and trying to relate it to what I know is, well, statistically, well, I know stats and stuff, but significant, well, the word significant means important, great, good. And so maybe, like, this could mean that the result is important or monumentous. But in science, this is not the case of how you interpret and understand what statistically significant means. From here and being clear of this. And really, it's just more, as I'll go through the rest of these slides, and I got some videos to make this a little bit clearer. This is more about it is, well, based upon the results, really, is this by just chance? What level of just by chance could have this happened versus not? And so really, is it a cause and effect that you're looking at between the actual data, or is it something that you didn't really happen? And so getting a definition in here, statistically significant is an estimate of the probability that the observed association or difference is due to chance rather than any real association. So remember, like, when we're talking about this association, we're talking about between two variables being, i.e., like your independent dependent, which is then telling you about your cause and your effect, that we're like, how are they actually associated? So you think the cause is happening, the actual effect. Are they really actually associated from the actual data? And is it just by random chance? So, like, in other words, like tests of statistical significance, which is something you can calculate. Again, this is quantitative reasoning and science and stats. And so there's going to be some kind of calculation off the data to give you back an actual value from it, and different tools that can tell you statistical significance. It describes the likelihood that an observed association or difference would be seen even if there were no real association or difference actually present. So say we're looking at the cause and effect of age and color preference, and if it wasn't age at all, it was just experiences people had or cultural things that played a role. That maybe wasn't age, but it was the culture you grew up in and the length of time within that culture or that group that had an effect. And so it's a combination of something else other than age. And, you know, sometimes when I'm leading up to this, why even have this graphic next to us? You can see it's a box and whisker diagram. And so you should know that each one of these represents different distributions. And so you're like, well, if we're looking at one where, like, we don't have the cause and we're measuring stuff off of the dependent variable, and one where we do have the actual cause and we know maybe larger is better, like, is this difference big enough to say we can draw conclusions, versus if they are closer, what could we draw and make a conclusion from? Kind of like going back to that example, like from note 6.2, the statistical examples, when we're talking about spending money. And you're like, well, if I had more money than what I want to buy like $100, and I'll have, you know, it costs $67, you know, I have $100, you know, I'm going to have $33 left overall at the end, versus, well, what if I only had $68 to spend because $67, I have $1, do I really want to spend all the money? I have a little bit left? And that's that feel. I want you to get the same thing as well, is that difference between our two sets of data that we're looking at and trying to use to analyze our cause and effect. Is it really a big enough change of when we measured, when we, like, without the cause and the dependent versus when we did? And is it big enough change? It's like, oh, it's just a coincidence. Maybe there's something else causing this to happen, and we're not along that right route of what we're actually doing. So statistically significant is an important thing to get across. And I want to give two videos, so a perspective of this, seeing from other people. And I like to pull in, because again, stats is not just from science, you use it from a wide range. And I'm hoping that these examples will jog your brain in different ways or connect with people different ways. So this individual here is coming more from a UX, and UX designers and everything else is coming from user experience. So say with exhibits to websites, to apps or programs you're working with and the interface you're working with, and they're worried about what is people's experiences along those times and trying to better the quality of a product. This can sometimes use a mixed methods kind of approach to research with qualitative and quantitative. And if it's the quantitative, then you're working with data, numbers, and statistical significance is an important thing. I'll have another video after that's coming from more of a science perspective, but I think this will give you a good point to begin with.
In quantitative research, we're always comparing things. That's what quantitative data, numerical data, is really good for. We also need to make meaningful comparisons in order to make sense of that quantitative data. Often, we use numerical data to compare two or more designs. Let's say that we're comparing our product's user experience to our competitors. When we compare the two sets of quantitative data for these products, we want to know if that result is reliable. That's what statistical significance can tell us. If the difference between two numbers is statistically significant, it's reliable. The result that we're seeing probably isn't due to random chance. Another way to think about this: if we ran the study in the same way a second time, we'd expect to see a similar result. So if we run a quantitative user research study and the data suggests that we have a better UX than our competitor, we want to know if that's a reliable finding. We can use statistics formulas to calculate the statistical significance for the relationship between these two data sets. If the formula says that we have statistical significance, that means it's reliable, from a statistics standpoint at least. We can probably trust that if we ran the study again in the same way, we'd again find that we're better than our competitor. But if we don't find statistical significance, there's some risk that our finding isn't really there. Maybe if we ran the study again, we'd find that, actually, our competitor's UX looks better than ours. Here's one thing that sometimes confuses people. Statistical significance refers only to comparisons. You wouldn't determine statistical significance for a single set of data. Let's imagine that I run a quantitative usability test, and I find that my users on average took 3 minutes to complete a task. I wouldn't be able to say that that 3 minutes is statistically significant. But I could compare the average time on task for my product to the average time on task for my competitor's product, and I can determine statistical significance for that relationship between the two products. Quantitative data is often used by companies to make decisions. Should we approve funding for a new redesign project? Where should we focus our redesign efforts? Which design option works best? Whenever you're trying to interpret numbers, make sure that you ask, do we have statistical significance for this finding? Is this comparison reliable?
So you can see there, like that good point which says like it's not, this is between variables that you're looking at and measurement. So it's two different data sets. So example you had is one data set being the usability of an app, like their company's app versus their competitors, and gathering feedback and seeing really, is it just random chance that say ours is better and how better, and being able to quantify and be able to talk about that. And so it's something we need to take into account beyond just that population size and that sampling. Is now this is going more into the analysis phase, is that once we're drawing our analysis and we see the differences between the actual groups, and we'll talk about this more in scientific method 3, well then we need to be careful that our results are statistically significant. And normally you'd be calculating that is based upon your data, you calculate it, you use specific tools for that, being statistical tools, and based upon the results coming out, you know what to do. In this course, it's going to be more as I want you guys to think about it as, has there been a large enough change that this is good enough of a result to actually draw any conclusions from. Stats courses and other science courses and social science and any research stuff would go deeper into this. But for now, I just want you to get that feel and you making sure that you make that difference. Not just that it's larger by 1, but is by 1 large enough, or is 10 to 100 to 1,000 large enough to draw your conclusions from it. So now this one here is more about like statistical significance and talking about stuff more in a science kind of terms here. And there's a longer video, but I'm going to stop when he starts talking about the null hypothesis, which is something that is important in science. But in the time we have for this course, I just want to condense how many facts I bring into place and give you guys a feel in a different way.
So I want to just review this idea of something being statistically significant. If we get a result in a study and we say that result is statistically significant, what exactly does that mean? I talked before about the idea that if I have two groups of people and I'm measuring something like their height. So I have some people, I'm measuring their height. I decide that I want to have two groups of people where the height is about equal. One way that I can do that is through random assignment. So I randomly assign people to two different groups. Maybe one of the groups I'm going to give some kind of a treatment to, and the other one is going to get no treatment, or maybe some kind of a placebo, whatever it is I'm studying. Maybe I'm studying how diet affects children as they grow. So at the beginning of the study, I want the groups to be about the same. I want to equalize things. So I randomly assign them to the two groups. And the idea is that through that random assignment, some of the taller people are going to end up in one group, and some of the taller people are going to end up in the other, and some of the shorter people are going to end up in one group, and some of the shorter people are going to end up in the other, and that should about equalize out. So some tall people should cancel out some short people. We should end up with groups that are about the same. So we might expect something that looks somewhat like this. Now the key here is that these are about the same, but there might still be some level of difference. And so after I've given my groups the treatment, if I see a difference at that point, I want to know, was that difference just because of randomness? Did I happen to put a few more tall people in one of the groups versus the other? Or was that difference caused by my treatment? And hopefully you can see some things like if the difference were larger, like if this were up here, if this were larger, then we would probably have more confidence that that was not simply the result of chance. More confidence, a larger difference, we would have more confidence that that's due to our treatment, and a smaller difference, I mean, all other things being equal, a smaller difference we would say is more likely just the result of chance. But we don't want to just sort of eyeball it and say, oh, that kind of looks small to me. We can actually calculate this mathematically. We're not going to do that here, but I just want you to get the idea that we can calculate this mathematically. We can calculate whether a difference is probably due to chance or probably not due to chance. And that is the idea of statistical significance. If we say something is statistically significant, we mean simply that the results are probably not due to chance. And so far we've talked about this just in the context of comparing two groups of people and saying, is a difference large enough to be a statistically significant difference? But this could be something we look at in anywhere where we're getting some kind of results where chance has an influence. If we were looking at a correlation, for example, if we were giving people, let's say that we're giving children vitamin D, or we're just measuring the amount of vitamin D that children are getting, and we're measuring their height, and we have some reason to think that there's a relationship between vitamin D and height, some kind of a linear relationship like this, and we're collecting data to see if that's true. But even if this is true, we still wouldn't expect all of the data to fall exactly along this line, because there's going to be other things that are influencing height. There are going to be a lot of factors other than vitamin D influencing height. So we wouldn't expect someone who takes a lot of vitamin D to be the tallest person around, but we might expect, if there's some relationship, that there's some consistency in the pattern, so that maybe the dots are not perfectly on the line, but maybe they fall close to the line most of the time, and we see some kind of a pattern. Now, again, the question is, if we were to just randomly throw dots on this scatter plot and there was no relationship between vitamin D and height, what are the chances of getting a particular result? And we can actually calculate that. And then we can say, okay, the result we got is that likely due to chance. This is very much like if you just take a coin and you flip a coin 5 times and you're asking, what are the chances of getting 5 heads in a row? Well, it's possible, but it's not particularly likely. So if we see a pattern in our results, like these dots falling very close to this line, we can say it's not likely that that is due to chance. In other words, we would say that is a statistically significant result. The results are probably not due to chance, so we would say it's statistically significant. And that's all that the term statistical significance means. Conversely, if we had dots just all over the place, then we would say this is actually quite possible that we get this kind of a pattern due to chance, and we can calculate that mathematically and say there's no particular reason to think that our results are anything other than just the influence of random noise. And again, we can calculate a concrete number for this. So we could say something like, for a given result, that there is a 95% probability that that result is not due to chance, or a 99% probability that that result is not due to chance. And I'll mention why I'm using those particular numbers in a minute. When you actually see this in a research report, this is talked about in sort of we look at it from the flip side. So instead of talking about a 95% probability that the results are not due to chance, we might talk about a 5% probability or a 1% probability. In this case, this is the flip side. This is the probability that the results are due to chance. Now, when you see these reported in a journal article, and rather than reporting it as percentages like these, we would usually see this reported as a decimal. So 5% as a decimal would be 0.05. 1% would be 0.01. It's exactly the same thing as saying a 1% or a 5% chance. And these are, just to give you some terminology you'll see used, these are called p-values. P-value is just a way of saying the probability of something being due to chance. So you'll see a result reported, like they'll say something like, we observed a difference between these two groups, and then they'll give you the p-value for that to tell you whether it was statistically significant. So they might say something like p equals 0.02 or p equals 0.34. Now, sometimes they'll give you the specific value like this. Sometimes they'll just say p is less than 0.05. What they're saying here is the probability that the results were due to chance is less than 5%. In this case, the probability, they would say probability is greater than 5%. In other words, there's a good chance or a good probability that those results are due to chance. So this right here would be statistically significant. This would not. And there's not this is a usual 0.05, a 5% chance or a 1% chance, sometimes a 1 in 1,000 chance. Those are the usual places that a scientist, in general, when we write articles, we say that's where we're going to make that cutoff point. That's where we're going to say we want to be at least 95% confident in these results not being due to chance before we place any real weight in them. And so that is why we say 0.05 or 0.01, but there's nothing magical about those particular numbers. That's just the convention. That's where we've said we'd like to be 95 or 99% confident that these things are not just due to chance. Now, there is one more piece of terminology that I want you to make sure you have tucked away in your brain, and that is something called the null hypothesis.
Okay. So what they saw is a good example of what I'm trying to get to for the course, especially with statistical significance, is when looking at data, and if there's a difference, how big enough of a difference do you actually get to a point where you can say it's not just by random chance? And in science, that can be quantified, coming down to calculating the statistical significance. And a lot of studies in the beginning will state what they expect their p-value to be, and you really want a low p-value, that saying it's 0.05 chance, there's only a 5% chance out of 100 that this was by random, and that can be an acceptable margin. Because you said, previous data, not everything will catch everything, is not 100%, but within that margin, that's high enough. That's if I have a 95% chance of passing the final based upon what you know of your grades before walking into it, I'd be a lot less stressed than, say, if I had a 5% chance of passing. Doesn't mean I won't, but it's going to be an uphill battle. And so here you're getting, when they talk about that, what that really means, that probability, and how this is then calculated at the end, is that you'll state it earlier, which is your margin to say it must be less than 5% for it to be accepted, and that'll be part of, say, your hypothesis testing and calculating your statistical significance from here. And one way of doing this is getting your p-value and how you calculate. There's other tools, but p-value, you'll see, you'll pop up a lot, is this final calculated value of how you get to that actual point. And you should expect to see that's an important thing to pick up upon when you're reading stuff through journalism and as mentioned, or if you're looking at articles that are coming out of science, or so those published papers. What does that actually mean? So example here, just saying p-value, something that you should remember, that it's a statistical tool calculated from the actual data. So the p-value tells us whether an observation is as a result of a change that was made, or is the result of random chance. So is it by your cause and effect in that change that you're making, or was it just random chance that this was happening? And this is if you've set everything else up right. Because realize you get a p-value, it's not the end result. If you don't set the right population statistics, you're not sampling, that your p-value be invalidated because the data it's being calculated from is wrong. We'll come to this later in the course when we talk about p-hacking and something to be aware of. But if you've done everything step strongly before this, then your p-value be indication of should I accept or reject my hypothesis? Or it's something that you should pick up from when you're reading from an article. So things here say like P is less than 0.05, statistically significant difference. If it's greater, no statistically significant difference. So maybe that's your margin, that you're only allowing that 5%, which you'll see pop up a lot for science articles, that if your end result and looking at the data and the change and the rest of your argument is that's not, if it's less than 5, boom, you can accept. If it's greater than that 5%, you just reject it. Even if it's at 6%, you just reject it outright. This is garbage, and I need to go back up to my steps and maybe change your hypothesis and change your experiment procedure and then go through it again. But at least you're getting feedback of how your innovation may or may not actually work, and then new data, how to innovate and grow off of that. And so take into account when you see these. For example, that article that the student found in that case study when they were designing their study about age and color preference that they found. So this paper, Changing Color Preference with Aging, a comparative study on younger and older native Germans aged 19 to 90. Now, from this first page, you'll see like there's sections down here and here that I've blown up to be in order, and I've highlighted that you'll see they start talking. You can see that quantitative and stats being used as a way to describe things. They start mentioning even stuffs of like the chi-square test, like up here. But you can see here they're saying, okay, all frequency distributions departed significantly from chance. So they're saying that the choices people are getting, so this is p less than 0.001. So this is not even 5%. This is not 1%. This is 0.1% chance. Like that's so small that you're like, no. Like here, but that's what they're saying. So when you see by chance p less than this, then they're saying, well, that is statistically significant, and it's a very small margin that this was just by chance, and it's calculated based on the data. So if I see that, I know logically the step before this should be that this was calculated based upon the data, and before that data should be how was sampling what it was done, and if that was done properly and the data was gathered properly, then this p-value should be proper. So another example of that deductive reasoning built in. Another one here says, like, in both younger and older adults, significant sex differences did not exist for the ranking of the most preferred colors. So P greater than this. So it was just really by chance. So the fact of changing, like in both younger and older adults, so not elderly in this case, that the gender didn't play a role in this. And so that's when they're saying P is greater than 0.2. You're like, well, from what they calculated is that they really wanted in a very narrow margin that this wasn't just by chance, so 2%. And what they found was a greater than this. So really they're saying it really wasn't an actual effect. But what they found next was, but there was evidence in the ranking of the least preferred colors. So the most preferred, gender didn't play a role, but the least preferred, something came up, and the probability of that difference was by chance is less than like 1%, is what they're saying there. So really this is more about when you're seeing that you know, okay, well, that's p-value, that's tied to statistically significant, that's about calculating the probability that these two things of the cause and effect were just by random or association between two things at all, variable A, variable B, was just by chance or not. And that the fact that you want it to not be by chance, you want a very low p-value for that to actually be acceptable in setting those margins earlier. And so for us, it would be, what is really the big difference between the data? So say, for example, if we go back to statistical reasoning part 1 and the example problems, we ended off with this example of the atmospheric chemist when they were taking measurements and seeing the effect of interstate freeway and pollution levels, because as pollution is already showed to be related to people's health, and the fact that we would want smaller values to be better, because smaller values or measurements meant like particulate, which means less actual pollution, versus larger measurements being that there is more pollution and it's worse for people's actual overall health. So if we start looking at the data, and we can't just calculate statistical significance based on data, we're looking at two. And the choice of these groups will become important. And we'll see this in scientific method 3 of when do you start deciding what those groups are and how do you do that to design your experiment better. But in this case, we had one away from the freeway because we're thinking, okay, remove the highway, remove the cause, and just take some measurements. and see what happens there, and then introduce where we take measurements next to the highway and see what measurements we had there, and just see, well, what's happening for this pollution, because maybe there was a third factor or something that was causing it, and based upon the data, they'd have to say what's their sample size and where they're sampling it from and why they made these choices and dig down deeper. But if we're looking at it, we'll see, is that difference big enough? And if we start looking at these box and whisker diagrams, well, we'd have these two data sets and see this difference between two variables, and when we go deeper into stats and we can calculate the p-value, and based on the p-value, make a decision. If we said in the beginning we wanted the association just has to be by less than 5% chance that it actually happened, and we calculate and we find that it does come out less than, we just automatically agree. Just like that buying problem. Oh, it's less? Yeah, good. It's greater? Bad. Like whatever you're looking at. For this course, and just you saw in the previous example, it's going to be more as, well, what's the overall difference can we see? Like we can see this one has a big skew. We know the interquartile ranges between here and they don't overlap. And we start looking at all the numbers and seeing a big enough difference. And we could decide before this, and maybe we should have stated, what is a big enough difference in the actual measurements that we're willing to actually accept? Maybe calculating a proportion and how close it is to that point that we make that actual difference. And so this is where that statistical significance come into play. So you have to realize in your design, and especially in the analysis at the actual end, that you have to make sure that the association you're actually seeing and trying to show is actually statistically significant enough. And then getting to that end of establishing your causality between here, the association, direction of influence, and the non-spuriousness. And that's a huge key point. So that's a big term to know and be able to talk about and clearly talk about and tie back to the statistical tools you're working with. Okay, but we'll come back to that in scientific method 3 and other examples that we work at as we're nearing, as we step through the course. Because we're getting closer to the end even at this data. So now before going on, we need to take into some other cultural things. And other impacts that could come into play beyond just our design, but of interpreting information and how maybe we represent it when we communicate it and engage with it, and even ethics. And so here I am pulling once again on that crash course because it has what I believe is a very good general introduction that you can then dig deeper into. So this video is more about science journalism, and when you're reading things at the end point of when it's maybe been published and then it's being interpreted through other news articles, how do you start taking that information in? And what does it actually mean? And you should know the steps that come before.
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. In this series, we've been talking a lot about how often you see data and statistics on the news and on social media. There are all sorts of studies and data sets promising the keys to a better life. Coffee's good for you. No, wait, it's killing you. So what do you trust? Journalism has many goals: to inform, expose, help people make better decisions about their communities and their lives. But the only way journalism matters is if people read it or watch it or listen to it. Journalists have to capture the attention of their audience and help them connect with the story. Case studies and observational studies can be a great source of material for an article or a podcast, but it's always important to look at both the quality of the science and the quality of the journalism. If there's a study without a control group or a non-randomized design, it's going to be less reliable. And if a journalist doesn't ask those questions or just doesn't include the answers in her story, how are you going to know? Back in 2015, newspapers around the world ran stories heralding chocolate as a way to lose weight. It sounds great, but turns out it wasn't good journalism or good science. A science journalist and PhD named John Bohannon created this story by doing a real randomized study, but one that was intentionally riddled with flaws. It was meant to be a way to show that academic journals would publish the very flawed study, and so would news outlets. The goal, writes Bohannon, was to demonstrate how easy it is to turn bad science into big headlines. And it worked. Once the study was published and the press release went out, journalists jumped on it. Bohannon says that many outlets ran the story without ever contacting him. Very few reporters asked about the number of subjects they tested, only 16, and no one, he says, reported that number. Also, says Bohannon, the stories that ran didn't quote any outside researchers for corroboration. And while it's disappointing that you can't add some Cadbury to your diet and lose weight, and maybe your aunt keeps quoting this study to you as she downs that 5th and 6th bonbon, but bad science and bad scientific journalism is not always that harmless. Most clinical studies base their conclusions on statistical tests that give researchers and the rest of us a quantifiable way to measure the evidence the study provides. For example, when a reputable doctor claims that ibuprofen increases the risk of fertility issues in men, it's because there was a study with a group that took ibuprofen and a control group that didn't, and the subjects taking ibuprofen showed a tangible increase in some measure of infertility. But which measure? And was the control group given a placebo? An article that you read on Yahoo Health probably is not going to tell you. For that information, you have to go to the original academic article, and those can be kind of dense. It turns out that this study did have a placebo control group, and it measured infertility in a clinically respectable way by measuring levels of fertility-related hormones. But these facts are important when considering how trustworthy the conclusion of a study is, and a lot of news articles don't have them. As a side note here, if this study was done in rats instead of humans, the conclusion that ibuprofen increases the risk of fertility issues in men would not be as strongly supported. But let's go to the thought bubble. Imagine that you're going about your morning as usual, sipping your coffee and scrolling through the latest news when you see an article with the title, "Miracle Food Causes Weight Loss." You want to fit better in your jeans, so you click through. You see that the miracle food is called Targ, and the results were statistically significant, so it seems legit. You jump in your car and drive down to the local grocery store and see that Targ is on sale, so you pick up the largest pack and start eating. You're already feeling stronger, but then you begin to experience side effects like heartburn and stomach ulcers and a weird desire to fight. The article you read didn't mention that when researchers considered the over 20,000 subjects, the weight loss was only about 1/10 of a pound more for Targ eaters. That's not very much, maybe not worth these side effects. When a study reports something is significant, you probably assume that means it's really gonna matter, but this isn't always the case, since significant means something different in statistics than in everyday English. And science journalists can misuse this confusion by not mentioning how big of an effect was observed. Thanks, Thought Bubble. We don't have time to read all the academic articles on even one topic that affects us. Take what gets called text neck, a condition that includes sore neck muscles from looking down at your phone and laptop all the time. A Google Scholar search for academic articles about text neck returns over 180 results, and that's only since 2013. There's no way that you could read all of those without exacerbating your already sore neck. So we need people like scientific journalists who can distill all those articles into digestible and engaging pieces for us to consume. It's helpful to be skeptical, but we should keep reading about science. When reading a science story, it's important to note a couple things. Who wrote it, who published it, who did the science, and who funded the science. If an article that tells you drinking Diet Coke is good for your teeth is on the Coke website, your suspicion should be raised, more so than if it was published by Scientific American. You should also consider who funded and completed the research the article's based on. If you read an article that claims a rare fruit juice will reduce your blood pressure and stave off cancer, and you see that study was funded by the juice company, be suspicious. Not every study funded by a company is inherently flawed. Science costs money. It can be expensive. And while there are sources of funding from governments and other neutral organizations, the reality is that often the people who are willing to pay to have the research done are the companies who have a vested interest in the results. Sometimes, to get the research done, researchers need to partner with these organizations. Privately funded research can be done well. Another thing to watch for in science and health journalism is whether the claims made in the headline actually match the claims made in the story. You don't see many stories with a headline like, "Ketchup may have mild relationship with weight gain in men over 40. Because who's going to read that? It might be accurate, but it's just not as flashy as, "Is ketchup making you fat?" There are a number of reasons we get these splashy headlines. Media outlets, from BuzzFeed to Goop to the old guard newspapers, are all fighting for audience these days. All right, maybe not the same audience, but audience. And that competition makes the super sexy headline really, really appealing. Sensational gets clicks. Content creators are under pressure to write and find what's going to get shared. The language of correlation is uncertain. and as such, less catchy. You'll also spot plenty of causation problems in science and health reporting. When you see an article that claims that doing yoga cures cancer, you should check to see whether it was an experimental study or whether the claim is based on correlation on a survey between doing yoga and not having cancer. Only experimental studies with randomized designs and control groups have a shot at showing evidence of causation, because personally, I can think of a lot of confounding factors for that yoga and cancer study. Now on to another way science can get mischaracterized. There are studies done on mice and rats that get reported as if they were studies on humans. And while a lot of medical and health-related studies get their start in mouse models, many of the treatments that work in mice don't end up being successful in their human counterparts. Similarly, you're going to see clickbaity headlines that say things like hydrogen peroxide kills cancer and list all the ways you can now incorporate hydrogen peroxide into your daily life. But what the title doesn't tell you is that these were in vitro studies, which means they're done on real cancer cells, but in a petri dish. In a very simplified sense, the cells were grown by themselves in a dish, and the substance of interest was put into the dish, and it killed the cancer cells. But in a dish, lots of things we consume every day will kill cancer cells, like coffee or alcohol. But they, even working in tandem, aren't gonna cure cancer. Anyway, these misguided hydrogen peroxide kills cancer headlines get shared around online, and people come up with alternative therapies that involve consuming hydrogen peroxide, which can be really, really dangerous, like dead dangerous. Science stories can make for great journalism, and they can give you something clever to say at your next dinner party. But anytime you hear a cable talk show host say the phrase, "scientists have found," or "a new study suggests," you should always look up that study to be sure, at least before you start spreading it around. And if the results of a study will cause you to make any changes in your life or your family's life, you should really go back and check the science. No matter how reputable the source, it's always important to be aware of these issues, whether you see it in BuzzFeed or The Economist. Articles often gloss over all kinds of details, the kinds of control group that was used, or whether the study was done in mice or monkeys, all of which can make a huge difference in how strongly you can take the claims of the study. And the bigger the life change you're thinking about making, the more in-depth your search for information should be. Adding a square or two of dark chocolate is not going to be a big deal. Trying to cure cancer with high doses of vitamin K, just because some study found it kills cancer cells in a dish, that is. So this doesn't mean all the science you read about on Reddit or watch on your favorite YouTube channel is wrong. It just means that you need to use statistical thinking to check which claims are reasonable and which aren't. In order to help us remember some of the rules of thumb we talked about today, our writer Chelsea came up with a limerick. And so without further ado, Crash Course's first original limerick. When a study reports correlations or has mice as its main population, the results it declares may not be quite fair. So be careful about generalizations. All right, let's see you do better. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Immingholt studio.
So, some good general life advice when you're hearing things in from any side you want to take into account. Doesn't mean refute everything, but know that if this is the final communication stage, there's a lot that's gone before this, and there's a lot of things that you should be looking for and asking for and questioning to validate this data, and realize there may not be one exact answer, but things are growing and evolving over time to the best that we could do now. So here now, this video goes more into ideas of ethics and science. Because just because we're doing science doesn't mean that every single thing is perfect. And everything from the past is perfect. And this doesn't mean that just because it was non-science, it was perfect. There's a wide range of things where all human stuff happens. And examples of Henrietta Lacks, the Tuskegee experiments, and ethical data collection is that you should be taking this account when you're doing this, and it works with a vulnerable population. If this is actually people, is this justifiable to actually do what you're doing? And when you're doing your study, and then anything with people, then, well, what are the proper ways you should know about doing this, and how is that vetted, and what process do you actually go through?
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. Today we're going to take a step back from sampling and regressions to talk about the impact of all that statistical gathering. We've seen that the interpretation of this information can have real lasting effects on our society, but its collection can also have lasting effects on the subjects. The process of gathering and applying statistics can affect real people's lives, which means there is a responsibility to gather and use this data ethically. Today we're going to discuss 5 stories. 4 of them are real, and all of them can help us learn where collecting data can go wrong and how we can help prevent these things from happening again. Our first story begins in 1822, when a young fur trapper named Alexis St. Martin got shot in the stomach when another trapper's gun accidentally went off. The wound was serious, but a local army doctor, William Beaumont, was able to stabilize St. Martin through a series of presumably painful anesthetic-free surgeries. But Dr. Beaumont couldn't close the wound, which left a small hole called a gastric fistula that allowed access to the stomach. St. Martin was out of a job, since it's hard to be an active fur trapper with a hole in your stomach. So he signed a contract to become a servant to Dr. Beaumont. In addition to traditional chores, St. Martin participated in all sorts of experiments at the whim of the doctor. Beaumont used the gastric fistula to study how the body digested food. He made huge strides in the field, including exploring the influence of mental disturbance on the process of digestion and correcting the long-held belief that the stomach digested food by grinding it up. When in 1838 the two finally parted ways, Beaumont spent the last 15 years of his life pleading with St. Martin to come back. Maybe unsurprisingly, St. Martin declined. Without this strange situation, the field of gastroenterology may have progressed more slowly. In fact, St. Martin's fistula was an inspiration to Pavlov, who used fistulas in dogs during his famous classical conditioning experiments. But all this progress came at a cost to St. Martin, and also to those dogs. One of the most important ethical considerations in research is whether humans who participate are able to feasibly say no. People with little power, resources, or money can be coerced into participating in experiments that they're uncomfortable with. Most research institutions have a committee called the Institutional Review Board, IRB, which oversees all the research at that institution to make sure that it's ethical. Voluntariness is one of the most important things that they check for. This prohibits people with undue power or influence over us from asking that we participate in a research study. For example, your boss or professor is limited in how they can ask you to participate in a research study because you might feel that you have no choice, that you have to participate. Otherwise, they might fire you or give you a failing grade. Ethical research needs to be voluntary, at least in humans. Animal rights activists argue that since animals cannot volunteer for a study, we shouldn't use them. In addition to their voluntary participation, subjects should also know what will happen to them during the study. This was not the case in 1932, when the Tuskegee Institute began a 40-year-long study on over 600 black men. Under the guise of free medical care, the men were secretly enrolled in a study to observe the long-term progression of syphilis. Over 300 of the men enrolled had the disease, but researchers failed to treat them with anything but fake or innocuous medicines like aspirin, even after it became clear that penicillin was a highly effective treatment for the disease. Late-stage symptoms of syphilis include serious neurological and cardiovascular problems, yet the Institute allowed the study to go on. Some wives and kids also contracted syphilis. In 1972, public outrage caused the study to close down when news of unethical conditions was leaked to the media. In 1951, at the same time the Tuskegee study was running, a poor tobacco farmer named Henrietta Lacks went to Johns Hopkins Hospital in Maryland and had cells from a tumor collected without her knowledge or consent. These cells were used to grow a new cell line called the HeLa line, which scientists used to do in vitro experiments. The cell's ability to thrive and multiply outside her body made the cell line useful to researchers. It's still used today for medical research, lending itself to cancer and AIDS research, as well as immunology studies like the one that led Jonas Salk to discover the polio vaccine. And in 1955, HeLa cells were the first human cells to be successfully cloned. Over time, the cell line and the discoveries it facilitated became extremely lucrative for researchers, but Lacks and her family didn't receive any financial benefit. These studies emphasized the need for informed consent. Subjects have the right to not only receive all the facts relevant to their decision to participate, they have the right to understand them. Many institutions require that information must be presented clearly and in a way that's appropriate for the subject's comprehension level. Even children whose parents are legally allowed to consent for them must get an age-appropriate explanation of what will happen in the study. This is incredibly important because it respects the dignity and autonomy of the subject, allowing them to stop research procedures at any time. That incentivizes researchers to design studies with more acceptable levels of risk. In all three of those stories, the research procedures didn't have any benefit to the patients. In 1947, the Nuremberg Code was created in order to establish guidelines for the ethical treatment of human subjects. One of the main tenets is beneficence, which not only requires that researchers minimize the potential risk to subjects, but also requires that the risk should be outweighed by potential benefits to the patient and the scientific community. The Nuremberg Code was created and implemented after the Second World War, during which horrifying experiments were conducted on prisoners in Nazi concentration camps. The Nuremberg Code lays out 10 principles to which modern-day studies still must adhere. These 10 principles stand as the basis for much of current research ethics and include things like voluntariness, informed consents, and beneficence. But as we settle into the age of technology, the application of these ethical principles can become more cloudy. Our last story here isn't real, but it illustrates the complexities of research ethics in the digital age. In the 7th season of the hit show Parks and Recreation, a giant internet corporation comes to the small town of Pawnee, Indiana, to offer free Wi-Fi to the entire city. Everyone gladly accepts. They like the free service. But when boxes of personalized gifts arrive at every citizen's doorstep, some become a little concerned because the gifts are perfect, fitting the exact interests of the recipient. Someone who collects stuffed pigs dressed as celebrities gets Samuel L. Jackson, and someone obsessed with politics gets the newest Joe Biden poetry collection. These boxes are perfect for the people who receive them. Eerily perfect. So how did the internet company know what each person would want? Well, in the show, it turns out that the free Wi-Fi came with a pretty high cost. Privacy. In exchange for the free Wi-Fi, the internet company, Grizzle, was collecting all data that was transferred over the network. This gets called data mining. And it may seem far-fetched, but it's happening right now. Not the gift stuff, the data mining. Grocery stores track what we buy with our rewards cards. Netflix keeps track of everything we watch. Amazon knows exactly what we buy, what we look at. And those terms of service agreements we click on without reading them when we download an app or sign up for a social media account, they often include some kind of stipulation. When we use free internet services, we're agreeing to pay not with money, but usually with our information. Facebook and Google offer their services for free in part because they're profiting off of our data. They might be using it for research or to customize our experience on the site so that maybe we buy or watch more stuff on Amazon and YouTube. They also use it to sell targeted ads, giving advertisers the opportunity to select exactly the type of people who are going to see their ads. And sometimes the way these ads are targeted can be pretty unethical. For example, companies discriminating based on age by specifying that job ads should only be shown to young people. Data is being used in ways that affect every facet of our lives. But since we're still in the beginning stages of this huge influx of digital information, we get to see the progression of ethics in this area unfold right in front of us. The laws that will protect your data and privacy, and mine, like the Nuremberg Code protects participants in scientific experiments, are still being written. And many of the same concepts are coming up. For example, using the internet, using Google, social media have become so entrenched in some societies that it's almost impossible to hold a job without them. And if that's the case, we need to ask whether it's ethical to require that users sign over their right to privacy in order to use them. Or like in most clinical studies, does that border on coercion? We also need to ask whether companies that use or sell our information be held to the standard of informed consent, which requires agreements to be in language that's simple enough for the user to understand what they're agreeing to, even if they don't have a law degree. Or on the other hand, whether companies should be exempt from this requirement if they only use the data internally. It's possible to draw parallels between data mining and the stories we talked about at the beginning of the episode, though admittedly, it's not quite as harrowing. Like Alexis St. Martin may have felt pressure to stay with Dr. Beaumont because he couldn't work as a fur trapper anymore. It can be argued, to a much lesser degree, that we use sites like Google or Twitter because we feel there's no other option as we try to remain informed in our hyper-connected world. And we might not be getting all the information we need to consent in an understandable way, similar to how Henrietta Lacks was not informed why her cells were being taken or what they'd be used for. These situations are obviously not exactly the same. And we, as a society, need to decide how to apply the principles of research ethics in these new digital spaces. As we move forward and gain the ability to do things like sequence an entire genome in days rather than years, we open the door for amazing advances in personalized medicine that could save millions of lives. But we also open the door for abuse of this sensitive information. The conversation about how to handle these types of situations is still going on. We're the ones who will decide what is said, and we're going to be the subject of those decisions. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Emigholtz studio in Indiana.
Food for thought. Something you need to take into account of this ethics and working with people and things like IRB forms that you'd expect also at like Mount Royal, that there are, if you're doing research and you're associated with Mount Royal, you have to get approved through one of these IRB forms to actually do this study and make sure it understands, and the importance of this, of what's been learned by mistakes that are done by science in the past. Henrietta Lacks. There's a really good book out there I would suggest. If you just search for Henrietta Lacks, you'll come across that book, and I think it's a very good one to read to see complex nature and wide range of like where we're going to and the ethics of how this affects other people. And if we're designing our experiment, we need to take that into account. If we're looking at an experiment, we need to take that into account. And it doesn't mean not using science and thinking about it as evil. It's a neutral thing, and it's the way the people are behind it and the choices that are actually made from it itself that introduce these factors. At least that'll be my own opinion. Boom, boom. So, now getting into other things of limitations, misconceptions, and misuses of statistics is that the way people interpret it and also the way people use it, you have to be careful. And this is part of the design and part of the analysis, that you've done things properly. You may have done your analysis completely properly, but how you gathered your data and sample size and population, therefore, wasn't done properly. So the conclusions you're drawing are invalid because the previous premise of the way that you gathered the data is false. And if you're analyzing results at the end point, or they're being communicated to you through journalism, well, you know that there should be previous steps before this and how you get to that. So this is just like a not super in depth. I've only got 9 slides or so from here, and it's just to give you a feel of some of the things you take into account, at least in this course. So, given the wide variety of possible statistical tests, it's easy to misuse statistics and data analysis off of the point of deception. And some people will do this. Even though it's political nature, other ways, the way they present it makes it sound like it's worthwhile. Associating someone's worth or death to cost value and associating that, like, is that worthwhile for that actual rate? And, some people could win it over by certain stats or realize there's more behind this, and being careful about it. And one reason for this is that statistics do not address systematic error that can be introduced into a study either intentionally or accidentally. The stats are just a tool that calculates from the data, but if that data was sampled or wrong or purposefully done to lead to misbias at the end, then that value won't be correct. I mentioned that quickly before, like the p-hacking, or sampling only one population because you'll get your answer if you sample and ask those people in your data, and then you do your normal analysis, and there you go, it got the answer I wanted, but that's not the point of this. And so being careful. And so some people have done this intentionally and some people accidentally, and you got to be careful and hoping that other people, when they vet it, will do it. And if not in the future, it'll be rejected and vetted, but it gets difficult once things are out there. So, for example, first interpretation, this is the end part of an actual result. Much earlier study, this is back in 1958, so we're far range off from where we're at now, like almost 80-ish years since then. And you can look up the paper yourself if you want to, but it's quite an old paper. But in their study, they found that individuals who smoked more than 1 pack of cigarettes a day, but had quit smoking within the past year, that within that population there was a death rate of about 198 people per 1,000 people, which is significantly higher than the rate of 157.1 people per 1,000 people. So these are all just metrics that's saying in the range of the population and measuring it from here. And this is more talking about, well, cause and effect of you're a smoker before this, and the cause of your death or something afterwards was due to like, oh, you smoked a lot, but then you stopped. And that there was a higher range in between the two. So if it was statistically significant enough. And I would say out of 1,000 people, if like, again here, the 40-ish more are dying, then well, that has an impact. And those are individuals who smoked a lot, but just kept smoking. So the effect of being a heavy smoker and then being a heavy smoker beforehand and like stopping smoking. So cause stopping smoking or not smoking relating to like, is it death? And without proper understandings of the study, one might conclude that quitting smoking is actually more dangerous for heavy smokers. But these are the end results, and you have to realize, well, that could be the sensational journalist article in the end. You have to dig deeper and see, what did the researchers say? What did they find and coming out of this? And were there new things that they learned? Because even the researchers in this actual paper found that offers explanations for the finding and saying things like, this is not surprising in the light that the fact that recent ex-smokers as a group are heavily weighted with men in ill health. And so maybe they stopped smoking because it wasn't, they had some kind of other illness or something major happen that was enough that they think they should be doing something. But at that point in time, they were already in a bad state, that there were many other factors that contributed to their death, and smoking could have been just one of them in that case. So it doesn't mean like, oh, you're a heavy smoker, keep smoking. It's like, well, okay, there's a likelihood that this is actually having an effect, but what else could be here? And this results showing that, well, they looked at these two, but then the fact that the end results from this was innovating, that was pointing towards new studies should be done into other factors of health considerations combined with heavy smokers that are quitting, that maybe if they're quitting, there's other things that need to be taken into account to deal with it. That maybe once they stop smoking, they turn to food, and food replaced that need, and that gained weight. There were some other ill factors. And so more research needs to be done, and that we can innovate off of this first study, but that we know that there was more behind just that one statement, that we can't just stick here. We need to step forwards and see, like, okay, well, what else is going on with this? So that's like heavy smokers who had stopped smoking, could be individuals who had quit because they were already diagnosed with an illness, thus adding systematic error to the sample. And without complete understanding of these facts, the statistics alone could be misleading. So even though you'll hear them, you can take that as a first step, but you should know that statistical tool was gathered based on data, just based on sampling in a population, and the fact that there could be confounding variables and like where they sample from, and maybe there could be other reasons, and like, well, how do you build up from there? So these studies isn't without use, you just need to take it into account. So the most effective use of statistics then is to identify trends and features within a data set. So this is what we're seeing, some statistical significance, that cause and effect in relation between the variables. These trends can then be interpreted by the researcher in light of their understanding of the scientific basis, possibly opening up opportunities for further study. So that they found one result, and that's not the end all, this is the truth, that's what it is. It's opening up and adding to that knowledge pools from there. And from their question, they had an idea of innovating, they evaluated it, and through the process came up with new ways of innovating, new knowledge that added to it, that maybe gives different ways that people can question what they're doing and looking overall. And so, like, a good one here, and I like to include this quote as well. This is coming from another article I'm pulling from, not from my own research, but it's from Andrew Lang, a Scottish poet and novelist, famously summed up the aspect of statistical testing when he stated, "An unsophisticated forecaster uses statistics as a drunken man uses lampposts for support rather than illumination." So this is really more meaning in being the forecaster looking at the data, that you're not trying to look at the data to support what you're getting, you're trying to illuminate and see what's happening. And this is why using the terms as we get deeper in this course, more people saying prove or like back up our argument. You're not saying it right, you're using it to test your argument, that you have your hypothesis, that you are gathering empirical evidence data and worrying about your bias and removing these cases and confounding variables to try strengthening the non-spurious case of your proving causality. And that based upon the analysis of that then data, you want to illuminate and find out, okay, yes, I will then accept it based upon my empirical evidence. That's not backing it, but my evidence shows that there is a correlation based upon the way I have done my argument and my reasoning to come to this point in time. Then other people can repeat that and add to that statistical significance that it's repeatable and it's not by chance. And more people can actually do this. And that the observed result I'm seeing is large enough to draw from there and backing everything up. And like this becomes a very important part. And even when you're illuminating it is, well, maybe you'll see new things you didn't see before. And that gives you a chance to think of new ideas and new innovations and new ways to do stuff and keep continuously growing off of that. And not just saying that knowledge will be stagnant, that you can change and grow stronger. That we accept certain things to be strong for now and then challenge it, but realize that's like living up to it or changing our perception and becoming humans in different ways. So, and like here, also with stats, all measurements contain some uncertainty and error, and statistical methods help us to quantify and characterize that uncertainty. Instead of saying, I'm kind of scared, you can say, I'm 90% scared. And you're like, okay, I understand what that means, versus I'm 2% scared. Maybe you're not so scared. Like you're quantifying, you're giving some terms and adding into that. That's important for science. This is why math is that language. Numerics, empirical evidence, quantities, and backing that up. If you're going to be part of that science culture, this is part of the way you need to change your vocabulary. And even if you're going to criticize it, you need to know and understand that culture, then know the points of where to criticize it beyond just your personal belief and what you don't like about it. This goes in any realm or anything you're looking at least in my opinion. And so this also, like this quantifying this way of talking, also helps to explain why scientists don't speak in quantified statements and why you need to do that. Instead of just saying larger, you're saying how larger, how much, what percent, what way, like 7% larger versus just larger, or what are you getting at? And this is the way I'll be evaluating stuff and seeing how you're talking as you progress through this course. How are you showing me that you're learning how to engage and communicate if you're thrown into a community of scientists or science-related people and quantified community, and what do you do with them? So, like, for example, for the quantified terms, like what I like to use is like no seismologist who studies earthquakes would be willing to tell you exactly when an earthquake is going to occur. Like, if I had that power of knowing, predicting exactly when that would happen, like, what would you do? You start becoming this overlord power of the I will create destruction and use the fact that I know exactly when that will happen to do it. Like, we don't know that level yet to be able to predict it. We'd like to. If we could, then we could react faster, but we just have to accept we can't right now. But if we at least know ways to quantify within range of that decision of is it strong enough of like a 5% chance of it happening in Calgary versus say a 62% chance of it happening in San Francisco, you'd react differently knowing those stats and being able to quantify that. And well, it may not happen, and that's what we would want, but if there's a higher chance, you should be ready for that. And decisions that are made, say, in how buildings are actually constructed, because if we're having higher probability of there being like earthquakes, then we should be really questioning the laws we put into place and restrictions based upon how buildings will be made, that if they come crashing down and the effects that would actually have. So a lot more times you'd get statements like there is a 62% probability of at least one magnitude 6.7 or greater earthquake in the 3-decade interval 2003 to 2032 within the San Francisco Bay region. Like, you can see where they're even talking about their more specific like population that they're sampling from and within what era. They're saying the probability of way it would actually happen. And I would say a 62% chance is high. Like that's even 50% chance. This is an earthquake, that this is more chances of it actually happening. And they're giving a range and interval and just saying, oh, it's going to happen at some point in time and somewhere. Too vague. And they're going specific, which ties back to their data. So with these statements, we could hear this. We should know where we can go back to, see where they're sampling, see how they've drawn this, and maybe see it's replicatable, or we can decide that maybe another study should be done to expand upon that. And no, it's not an end-all be-all, but if there's enough of these things agreeing, we can step forwards with this. So it's ambiguous, but it's like it's very confident in the way that it's being explained, the way that we're actually working with this data, and it's a way that if you are asked to, like I'll ask you to talk about what thing is science and how you talk about science, and you talk about your answers, you have to quantify it in some way to back that up with other stats and use that as part of your argument. For this course, you may not be perfect, but you can take an attempt because this is not a... So I just want to end off really quickly by saying again, the idea of why we need to know about stats and understand is not just to be able to interpret things from a journalism side, but understand the culture, is that we need to take into account when designing stuff within your actual experiment,